Alright, let's talk about the periodic table in terms of periodic trends. Well, what is a trend? A trend is something that we can observe in things that have similar properties. And periodic trends are just like that. But before we talk about the periodic trends, let's talk a little bit about the periodic law. The periodic law states that when elements are arranged in order of increasing atomic number, the elements with similar properties appear at regular intervals. They appear at regular intervals. And we've got an example down here in terms of we've got increasing atomic number, and we're looking at the atomic radius in picometers. Pico we really didn't study. Quite a small measurement. We've got atomic number 1, and it, of course we know that's hydrogen, and the atomic radius is slightly smaller than 50. Helium, atomic number 2, slightly larger than 50. We go to the next element, atomic number 3, lithium. We notice that we have a big change in atomic radius. Well, why is that? We're actually going to look at some of these trends today. Talk about some of them today. Let's talk a little bit about chemical reactivity, or something's ability or desire, I suppose I should say, to form a chemical reaction. The ability to form a chemical reaction. Phone's going off. We group, or we call these families, and these families, which we have different colors, and we're going to talk about the names of the families on the next slide. These families are very similar in how they react. As a matter of fact, I believe I've showed a video of the alkali metals, and we're going to talk a little bit about that. I'm going to show one, and I'm going to put a link on Moodle to the alkali metals, and their similarities in reacting. But the reason they react, or the families react the same, is because they have similar valence shell electrons, or the electrons that are used in bonding within their outer shell. So that leads to similar chemical properties. Now, we have several groups that we can talk about. This first group we know as the alkali metals, very reactive. Hydrogen sometimes considered part of it, sometimes it's not. Remember, hydrogen is kind of an odd little element. Lithium, sodium, potassium, rubidium, cesium, francium are all very reactive, as you have seen or will see in the alkali or the videos from YouTube that I'm going to show you. Second group are alkaline earth metals, still quite reactive. For example, calcium reacts quite warmly with water. Not quite as reactive as the alkaline earth metals, quite reactive. The transition metals are typically quite stable. It's what we use for we use for gold. A lot of our precious metals come from this transition metal. We call this whole what we refer to as the D block, the transition metals. Then we have a few over here. Actually, these do have names, but we're not going to talk about the names in this class. The next group we're going to talk about are the halogens, and they're quite reactive. Fluorine, of course, is the most electronegative element, which we're going to talk about. And we've got the noble gases. The noble gases are quite unreactive, but we do know that they can react. Two things that we have missing on this slide are the lanthanide and actinide, or the F block elements down at the bottom. You should remember those. Now let's talk a little bit about other properties. Let's talk about the atomic radius of an atom, or the size of an atom. We can think of an atom as sort of like an apple. You've got a core in the middle of it, or your nucleus, and then you've got that fruit, or the electron cloud, building around it. The point from the nucleus, or the core, to the outside shell is considered the atomic radius. Just like you studied radius or radii in geometry, this is very similar. Now, the first ionization energy. Let's talk a little bit about the first ionization energy. The first ionization energy is the amount of energy, or the energy required to remove one electron from a neutral atom. The amount of energy, whether it be light, heat, or whatever, required to eject one of those electrons. Now, when it ejects one of these electrons, we consider that an ion, which we're going to talk a little bit more about later in this presentation. An ion, and if um, an atom loses an electron, it loses one of its negative pieces, so it now has more positive pieces, so that is now a positive ion. We're also going to talk a little bit about melting and boiling point and how that has to do with intermolecular forces as well. Now, the atomic radius. Let's go a little bit deeper in that. I've actually already shown you this graph. The atomic radius increases from right to left, so the larger ions are going to be on the left, and it also increases down. Well, down makes sense because we keep adding more and more electrons to that outer shell, so we keep making the electron cloud larger and larger. Why does it increase to the left? Well, okay, why is it larger going down? Higher energy levels have larger orbitals, or they have more electrons. We also have shielding that occurs, which means your core electrons, or the ones that are not in valence, block the attraction between the nucleus and the valence electrons. So your valence electrons don't have near as much nuclear pressure on them, pulling them towards that core. Why is it smaller now to the right? Well, we have an increased nuclear charge without additional shielding pulls those electrons in tighter. So the greater the negative charge we get on the outside, the more attraction we actually start getting for that positive core or that positive nucleus on the inside. Now, the first ionization energy. Ionization energy of an atom or ion is the minimum energy required to remove an electron from the ground state of the isolated atom or ion. Now, the first ionization energy increases as you go up, and it increases to the right. It is much more difficult to pull an electron from a smaller element than it is a larger element. A larger element has a lot more electrons. It really doesn't notice if you pull one away. Think about your bank account probably compared to your parents' bank account. If you pull out $100 out of your bank account, you're probably going to notice it a whole lot more than if your parents were to pull $100 out of their banking account. They have more, therefore it's not as noticeable to them. You have less. You kind of keep up with yours a little more closely. Why is it opposite of atomic radius? Well, in small atoms, electrons are closer to the nucleus. When those electrons are close to the nucleus, you have that positive and negative charge really attracting, and you have a strong attraction to each other. Why do we have small jumps within each group? Well, stable electron configurations really do not want to lose an electron. They really do not want to lose an electron. Now, successive energy jumps, so this is our second or third ionization energy jumps. A large jump in ionization energy occurs when a core electron is removed. All right, we can easily remove, or I say easily, it is easier to remove a valence electron, which are the ones on the outside. Remember, valence electrons we use in bonding. It is easier to remove one of those than it is to remove one of those core electrons, or one that's really close to that nucleus. Why is that? Well, you have a stronger attraction. Okay? What? Alright, just a little bit different. My slide jumped around. For example, the first ionization energy of aluminum. Aluminum, we know, has 3 valence electrons. Now, the first electron, it takes 577 kilojoules of energy to pull away. Second electron, it takes more energy to pull away. The third electron, it takes a whole lot more energy. Now, aluminum has 3 valence electrons. What about when we go to the fourth ionization energy, one of those core electrons? How much energy is going to be required? Well, if we pull away a core electron from aluminum, the amount of energy required is enormous, 11,600 kilojoules. Very, very difficult to do. As a matter of fact, it's even difficult to pull that first electron off of aluminum. It takes a very electronegative element to do that. Let's talk a little bit about melting and boiling point. Melting and boiling point is highest in the middle of a period. Okay, so the middle of the periodic table, you're going to have a higher melting and boiling point. Well, what does this have to do with? Well, this has a lot to do with intermolecular forces, which we're going to talk a little bit more about in Chapter 10. Atomic radius. Okay, you should remember that the atomic radius is the distance from the center of an electron, or the core, or the nucleus of an atom, to the outside of the electron cloud. Now, if an atom loses an electron, it becomes an ion. Okay? An ion, you should remember, or you should know now, is an atom that has lost or gained electrons. So what we're saying is the number of protons and electrons are no longer equal. If an atom loses an electron, obviously it's going to get smaller because you're taking something away, and it becomes positive. We refer to positive ions as cations. If it gains an electron, or if we put something negative back into it, it gets larger. If we're putting more into it, it's going to get larger. So an anion, is what we refer to it as, is an atom that has gained an electron. An atom that has gained an electron. All right, let's look at a couple of examples. Which atom has the larger radius? Beryllium or barium? Beryllium or barium? Well, we should know that the atomic radius increases as you go down because you're adding more and more electrons. So barium. Calcium or bromine? Well, calcium's up at the top. Bromine is towards the right of it. So calcium is going to be bigger because, again, atomic radius increases towards the left. Which atom has the highest first ionization energy? Nitrogen or bismuth, and we have barium or neon. Well, nitrogen is going to be nitrogen because the ionization energy increases as you go from bottom to top because it's harder to get those core electrons or those electrons away from the smaller atoms. And is it going to be barium or neon? Well, it's going to be neon because neon, the ionization energy increases as you go from right to left because neon has a fuller valence shell, so it's harder to get those electrons away from it. Which atom has the higher melting or boiling point? Well, we have to look and see which one's closer to the center. Lithium or carbon. Lithium's in group 1, carbon's in group 4, so we're going to say carbon on that one. Chromium or krypton. We're going to have to say chromium rather, because chromium is almost in the dead center of the periodic table. Which particle has the largest, or which ion has the larger ionic radius? Well, sulfur or S2-. Well, this sulfur has had electrons added to it. So is the sulfur atom or the sulfur ion going to be larger? Well, the sulfur anion is going to be larger because it has more added to it. Aluminum or aluminum 3+, which one's larger? Well, aluminum, since it's positive, it had to have 3 negatives taken away from it, so the aluminum atom will have a larger radius. This is just a little bit of an overview. We're going to look more closely at this in class with our coloring of our periodic table diagrams.